Welcome back. Let us resume our discussion on the variation in mismatch and related issues. We just now discussed the implications of threshold voltage variations on the inverter transfer characteristics, and we saw how is it going to impact the interfacing between the digital inverter and the preceding analog stage, and we tried to justify the use of the second stage in meeting the full swing requirement and having better robustness, and also making sure that the static power dissipation in the interfacing inverter is limited. Just like the threshold voltage distribution has has its impact on the characteristics of digital CMOS circuitry, it has even more severe, more critical impact on the performance of analog circuitry. So, threshold voltage mismatches can play a very important role in the differential amplifier operations, where we are expecting that the pairs, the transistor pairs constituting the differential amplifier, they are very well matched. So, our differential amplifier analysis assumes that the transistor pairs are well matched, their VT, all the device parameters, lambda, everything is well matched, and that gives us a good differential amplifier. It ensures that the CMMR ratio is large, the differential gain is large, and the common mode gain is lesser. However, we have seen in the beginning that if you are having a significant mismatch between the transistors, you can have poor CMRR as well as PSRR. You can end up converting a common mode disturbance into differential signal because of the mismatch in the input pairs or the load pair. So, whenever they are paired transistor and you are having mismatch between them, it can lead to significant amplification of the common mode signal. Even when we are operating the amplifiers as comparators or as feedback amplifiers, once again those mismatches can play an important role. For example, here in our particular example we just studied, we came up with an architecture where we are using two comparators, CP and CN, and we know that the individual pair CN and CP, individual pair of the MOSFETs in CP and CN, they can have threshold voltage mismatches. So, let us see first of all what is the effect of the threshold voltage mismatch in the transistor pair, and finally, how does that affect our overall operation in this architecture that we have chosen. So, let us consider the first differential stage itself. Ideally, if I am looking at the differential input with single ended output, and suppose we also include the second stage over here. So, of course, ideally we understand that considering the process variation, we do not have a very well defined control on the output DC potential, but suppose we have sized it such that the DC potential over here is VDD by 2. Suppose we have some mechanism through which we have fixed this potential to be VDD by 2, or assume that when the input signals are close together, the output expected is VDD by 2. So, when both the signals are exactly same, the output expected is VDD by 2. Now, when we know that we have derived the specification for the gain of this amplifier when we are operating it as a comparator based on the ADC application specifications of resolution and so on. So, there we saw that if there is a significant difference between these two signals, delta V, say in our case 15 millivolt, the output should be completely going up or down to VDD or ground respectively. However, if there is a significant mismatch between these two transistors, how is the overall transfer characteristics going to change? So, a VT mismatch in the transistor can be represented as a voltage in series with the gate of the MOSFET. So, I can add a delta VT in the gate of the MOSFET, and how does it capture the VT mismatch? So, if you are having the ideal MOSFET where you do the ID VGS characteristics for example, and you get a certain curve for the ideal MOSFET without any mismatch, and then in the second case, so this is the nominal VT of the MOSFET that you expected, but in the second case you are having a device which is having a slightly larger delta VT. So, what will happen? The entire curve will shift slightly towards the right. On the other hand, if the delta VT is negative, the entire curve will shift towards the left. So, I can capture this shift in the characteristics by modeling the mismatch or the change in VT by a small voltage in series with the gate of the MOSFET by putting a delta VT over here. there are many other parameters in the MOSFET that can vary. Vt is of course a particular parameter coming in the model. In the actual physical device, there are so many different parameters because of which other characteristics can also vary, but in order to capture the parameter variations, generally delta Vt or Vt mismatch is a good way, and generally in order to capture the effect of all other physical parameter variations and mismatch, we model all of them, we can model all of them in the form of a Vt mismatch. You can also have many different physical parameters contributing to this Vt mismatch, but for the time being assume that ultimately some process mismatch or some process variation is leading to this delta Vt change, and we want to see the effect of that on the comparator operation or the amplifier operation. So, as long as the open loop operation is concerned, and if we say that say this is M1 and this is M2 and this is having a Vt which is slightly larger as compared to the other device M2. Now, if we have Vref over here and now we assume that the Vt of this device is larger, in case of perfectly matching case, I would expect that when this input approaches Vref and crosses Vref, the output should be going high. So, if I look at the ideal transfer characteristics when the Vt's are very well matched, I am looking at V in. Whenever V in is crossing the Vref, I should have the comparator output transiting from low to high. These are ideal characteristics, but now if I have a delta Vt coming over here, that means the effective Vt of this. So, the way I have drawn is the positive voltage over here, that means the effective threshold voltage of this M1 has been reduced. So, if I take the polarity over here plus minus, then it is increased. Why? Because if the polarity is plus minus over here, that means a smaller gate voltage over here will be able to turn it on more strongly, because you are having a delta Vt positive over here. So, here also if I am having this delta Vt positive from here to here, that means if you are having another gate voltage Vg that you are sweeping, this Vg plus a positive delta Vt added over here will mean that the effective gate voltage here is larger. As a result, the current will be shifting towards the right. For a given VGS, the current will be larger, and as a result, it will be shifting towards the left. So, we should just take care of the polarity. Now, likewise here, if you are having a delta Vt sign over here plus minus, that means if the for a given V in, the effective Vg experienced by this MOSFET is larger as compared to the M2. As a result, what do we expect? It will be tripping at a lower value of V in. So, the transfer characteristics will be shifting this way. On the other hand, if it was negative, that would mean it will require larger V in to match the same Vref. As a result, this is Vt lower, and if you have the other opposite scenario, the Vt will be shifting, or the characteristics will be shifting towards the right side. This is for Vt being higher. And definitely, if your delta Vt becomes comparable or larger than the resolution that you are targeting, say 15 millivolt in our case, that would mean that you can have error in the overall digital value that you are getting. For example, if I expect that the overall ADC transfer characteristics is something like this, you have the analog values along the x axis. So, this is your analog sample V in, and corresponding to the y axis you are plotting the digital word. So, if these are the intervals. So, this is your delta V, and just let me call it delta. So, this is delta, this is 2 delta, this is 3 delta, 4 delta, and so on. So, and corresponding to that I have the digital words. So, if my signal is greater than delta, then I am having the word something like 001. If I am my signal level is higher than delta. So, if I say my signal level is higher than delta, for this entire range signal lying between delta and 2 delta, the output is 00001. This is the binary output that I am depicting. If my signal level is between delta and 3 delta, my digital word is over here. So, I can write it 01000 and so on. Likewise, if the signal is between 3 delta and 4 delta, my signal, the digital word encoded is 30011 and so on. So, this is the digital word corresponding to the corresponding analog value. If the analog value is lying between delta and 2 delta, it is going to encode it as 0 0 1. If it is between delta to delta, 1 0 1 1 and so on. This is the expected value, and we can go on. So, this is the staircase case approximation. We of course have some errors. We have a quantization error, of course, because for this entire range of the input signal, the output is same 0 0 1, whether the signal lies here or here, it is always going to be encoded as 0 0 1. So, that leads to an important ADC parameter, which is quantization error. We may deal with that a little later, but now assume that this is the characteristics we expect ideally, but now the comparator is having some delta Vt shift, and suppose the Vt is negative for M1, input signal is coming over here, and the Vt of M1 is lower than the Vt of M2. That means, the comparator will be tripping from high to low in our case for lower values of V in, right. That means, values even lower than delta will end up having the high level over here. So, you can have the entire characteristics getting shifted. Suppose the delta Vt is just around 15 millivolt, higher than 15 millivolt or 20 millivolt. So, in that case, the shifted characteristics will be something like this. So, if the assuming that delta Vt is say 20 millivolt. So, it is higher than delta and lower than 2 delta. So, in that case, the overall characteristic gets shifted towards left, and we have this as the new characteristics, right, because now the signal V in is getting effectively added with this delta Vt, and as a result it will be crossing these delta references for lower values of V in, right. So, effective potential over here becomes V in plus delta Vt in that case, and as a result the whole curve for the ADC characteristics gets shifted towards the left. Likewise, if you have larger mismatches rather than 15 millivolt, if it is 30 millivolt or 35 millivolt, there will be 2 step shift. So, the entire characteristics will be getting shifted by 2 steps. So, in that case the characteristics may look like this, right. So, first of all we are having a shift in the overall characteristics, we are having error in the exact value, and also we are losing some of the quantization, because here the values we cannot have values lower than or we cannot encode the values lower than a certain magnitude, say 3 delta. So, if this is the condition, we are having a twice 2 step shift, then we cannot encode the values which are within the range 0 to 2 delta. That will give you that you are basically losing that information, because 0 to 2 delta is lying out of range of this characteristics. So, we are losing that information of around 2 delta voltage. So, all the signal levels lower than 2 delta are not getting encoded correctly. So, that is one disadvantage, and another disadvantage is that the characteristics of the digital word recorded are higher than the expected exact values. So, if I am say having only say one comparator, then this is occurring as an offset in the overall amplifier or overall ADC characteristics. So, we can test the ADC and we can find out what is the overall shift, and in the digital domain we can subtract that shift, and we can still retrieve the required value, at least for the range which is getting captured. The lower 2 delta which is getting missed, that we cannot capture, but the remaining can be obtained by just subtracting that 2 delta digitally. If you have the digital word, you can subtract it always if you know that this is offset. This is clear? Now, the problem is that in general this delta may not be even constant, the shift may not be even constant, the delta Vt that we are adding over here, that may not be constant, this can vary over time. So, there are some device effects because of this offsets can vary over time, there can be time dependent shifts in these offsets. If a static offset which is constant in time, then we can basically read out the digital data, and we can calibrate it, and we can find out by testing that okay, this is the offset this amplifier is having or this comparator is having, this is the delta Vt this MOSFET is having, and based on that I can go back in the digital domain and subtract those lower 2 bits values or add those lower 2 bits value to get the correct digital value. That is possible, but in general it can keep shifting over time. The digital domain does not have the information about it is not really tracking the time dependent shift in Vt. So, that can lead to a lot of problems, it can lead to inaccuracy on the fly, it can lead to inaccuracies in the recorded data. In our architecture, we have another issue that is also coming up. We are using two comparators, the PMOS input device and another with NMOS input device, and their characteristics can get shifted by maybe similar amount in opposite direction. If that happens, suppose NMOS characteristic gets shifted up by 2 delta and the PMOS characteristics get shifted down. You can have the delta Vt becoming negative, plus, minus. As a result, the characteristics can shift down. So, suppose this is the characteristic that the comparator with PMOS input device is having. So, it is very different from, or significantly shifted with respect to the characteristics that the NMOS comparator is having. Therefore, for a given input signal, we can see that the output of the NMOS and the PMOS comparator will be different, and as a result you are going to have different digital words coming out of those two. If they are operating in different regimes, so for the lower voltages, as we said, the PMOS will be used. For higher voltages, the NMOS input device will be used, and at the juncture we can have that, okay, means this is the point beyond which the NMOS will be used. If the input voltage is higher than certain value, it will be going to the NMOS comparator, and if the input voltage is lower than this boundary, we will be using the PMOS. So, at boundary, once again we can see that the NMOS will be the PMOS input device will be giving a different result, and NMOS input device will be giving a different result, and therefore, you have a mismatch between their results. If you are using, at some point you are using the NMOS comparators output, you are using other time you are using the PMOS comparators output, their mismatch can result in different effective digital words for similar magnitude of the input. And therefore, when you are combining the results obtained with the help of NMOS comparator and the PMOS comparator, once again it can lead to errors, relative errors, and once again if those two errors are changing over time, shifting over time, that becomes even difficult to track. So, in general, if you are, for example, going for the sizing of the transistors, you are trying to reduce it to few micrometer, in that case the mismatches can further aggravate. You can have mismatch between the two PMOS transistors over here, the NMOS over here, and as a result the overall effective mismatch between these two transistors in the pair, it can lead to a larger effective offset voltage, and good value will be at least it can range, it can go all the way up to few tens of millivolt. If the fabrication layout is not done properly, the mismatch can be pretty bad, it can go to few tens of millivolt, and in that case our transfer characteristics for the NMOS and PMOS comparator can be different and vary over time, and therefore, there will be a time dependent error in the signal that you are recording. So, this is very undesirable, and definitely we would like to have some mechanism through which it can be compensated. So, before we go there, we would like to talk a little bit more about the overall offset of the amplifier. Any question before we proceed further and discuss the offset in some more detail? So, first I am trying to show the effect of the offset. If you are having such a delta Vt mismatch, at least in this input device, what is the effect of that on the overall ADC transfer characteristics? And then let us have a little bit more discussion on the offset for a single ended output or differential output. What is the difference? How does it come into picture? Any question till this point? Amplifier over here, it is single ended output, and of course, here we do not have a mechanism of defining the DC potential. We have assumed that, okay, if the two outputs are very close, output will be close to VDD by 2, and one of them going high by delta V, which is 50 millivolt. I expect that this is having sufficient gain, it will be able to drive the output completely to VDD or completely to ground. That is what we have assumed. Now, if I look at the delta Vt, so basically it is shifting the characteristics in a certain fashion depending upon the polarity of delta Vt, and this delta Vt I can replace it by V offset, which basically is going to capture the effect of delta Vt of the upper two devices also. How do we do that? just like we have the concept of input referred noise, we can refer the noise contribution of all the devices at the input. Likewise, we can refer the delta Vt contribution of all the devices at the input. For example, if you are having say if you are having say certain delta Vt over here. So, you are having delta Vtp and also you are having certain delta Vtn. So, I can take the superposition of this individual delta Vt and find out what is the effect on the output voltage because of this delta Vt coming in. For example, if I assume, for example, let us take the effect of this delta Vtp first on the output, assuming small signal, assuming that this delta Vt is small as compared to supply and small signal is valid, I can find out the gain from this point to the output. So, let me call this A P to out, A P to out times delta V P is the delta V out 1. So, as compared to the nominal value, what is the nominal value? Nominal value was equal to this value is expected to be VDD minus VSG of P, and depending upon the threshold voltage we can determine what is the VSG. So, you have a certain bias current and it is going to generate certain VSG, and therefore, this under perfectly matched condition, these two being matched, we have seen that these two drain potentials should be similar. Therefore, they will be equal to VDD minus VSGP. This is the DC potential expected. But now, if I assume that there is a small delta Vt coming over here, because of that, whatever is the gain from this point to the output, it is just going to act like a common source amplifier over here. We have a input device, and then in the common mode analysis also we have done this kind of analysis. This is acting like a common source device, source grounded, you are applying some delta Vtp, it is going to lead to some voltage gain over here, and I can call it delta V out. AP out means from the P gate to the output, they have a gain AP out, which is the gain of this common source amplifier from this input of the gate to the drain, assuming that others inputs are all set to 0. So, for this side it is just like a common source amplifier, PMOS input device, this is the output point, and for that I have certain gain AP out times delta V equal to delta V out 1. Now, if I want to refer it to the input, what is the equivalent delta V at the input which would produce the same delta V out 1. So, in that case I can divide this V offset input, that is the input referred offset equal to this delta V out 1 divided by A differential, which is the differential gain of the circuit. What is the difference between these two inputs which would produce the same shift or same change in the output as compared to the DC bias point? That becomes my input referred offset. So, just like the noise case, we have seen that the input referred noise mostly depends upon the first stage, right, because it is getting for the second stage the overall mismatch effect is getting divided, or over the noise is getting divided by the gain of first and second stage. Likewise, for the two stage amplifier or comparator that we are using, the overall offset or the input referred offset will be dominated by the offset of the first stage. Second stage offset, if we want to refer it to the input, it will be divided by the gain of two stages. So, as compared to that of the first stage, it will be significantly suppressed. So, the mismatch in the first stages, the PMOS pair and the NMOS pair, they are going to play important role or dominant role in determining the input referred offset of the amplifier, not so much for the second stage, similar to the noise effect. And therefore, I can for the external user, if I have designed this transistor and I have characterized this, that this is the input referred offset. So, I can model this input referred offset as an ideal perfectly matched differential pair where all the transistors are very well matched. I have taken the contribution of mismatch in these two pairs and then added them together over here. So, effectively I am having some V offset which is present in the device. So, this V offset is having the effect of delta Vt or the mismatch in these two devices. They are anyway directly coming at the input because there is anyway the input device. Whatever is the delta Vt mismatch over here, it appears as it is over here. For the output, the load devices, we are first calculating the output change because of a particular delta V over here, and then referring it to the input by dividing that delta V out by the gain of the first stage. So, this is the essential concept of the offset or the input referred offset, and to the external user I have this as the ideal amplifier which is perfectly matched, and the effect of mismatch in the differential pair transistors are being modeled with the help of this V offset inserted in the in one of the terminals. So, in this case the positive terminal. So, in general I can model this as an offset voltage V offset inserted in series with one of the terminals. I can either insert it over here or here, and that depends upon the overall polarity. So, I can model the overall amplifier by an ideal amplifier, extract its offset out, just like we do with the noise. We extract all the noise at the input referred noise, and the rest of the amplifier is noiseless. So, we are doing the same thing with the offset, and then we can it is convenient to analyze the effect of such an offset or delta V on the amplifier characteristics, on the output DC point, or the signal swing, and so many other things that we are going to get. So, this also plays an important role in the front end. So, we have not yet discussed its implication on the front end design, that is also going to be there, but for the time being we have started this with the comparator design. We will revert back to the front end design also, and we will try to see what is the effect of offset on the front end design, especially for the fully differential case, and what can be the solutions to those. Likewise, in the comparator the solutions may be slightly different. We can see what are the pros and cons of this offset. So, overall characteristic point of view, this is what is going to happen. This is the overall implication on the architecture that we have chosen. And next we need to look into the solutions at circuit level or architecture level, which can help us in mitigating the effect of this offset and get back to our original ADC characteristics. Any question before this point?
Can you explain the shifting of that binary output versus delta?
This? Yes, so, here as I said, you are having the ramp voltage, right. So, what is the mechanism of the ADC that we are having? It is charging the capacitor using a ramp voltage, and at some whenever this ramp voltage reaches the V in sampled, it should trip. But now suppose I am having this delta Vt added to the M1, it is representing the offset. So, in this case the V in plus delta Vt will effectively present a larger voltage at the gate of M1. So, rather than tripping here, it will trip here. So, as a result, if it is going to trip here, that means the digital count is lower than what I expected or the ideal expected value. If likewise the delta Vt was negative, it would trip here, and the digital count would have been higher than the ideal value. So, this is the digital, for a given analog input I have drawn the digital values. This is the characteristic between the analog input and the binary digital output of the ADC. If the input is between 0 and delta, the output is all 0, 0, 0, 0. If the input is between delta and 2 delta, output is 1, 0, 0, 0, or in other words 0, 0, 0, 1. If it is between delta and 3 delta, 2 delta and 3 delta, it is 0, 0, 0, 1, 0, and so on. So, this is the characteristics, transfer characteristics or input output characteristics of the ADC. If now if I have this scenario, then the entire curve either gets shifted up or down. Is it clear? Any other question? And the more severe thing is you are using two different comparators. For NMOS and PMOS, the shifts can be opposite, and in that case the mismatch effect is even worse. And it can other point is it can shift over time. So, there can be time dependent shift in Vt. There are some mechanisms through which we can have time dependent shift in Vt, like temperature. Temperature changes, Vt can change, and as a result the PMOS and NMOS have different temperature coefficient for the Vt, and that can lead to different shifts in the Vt. Likewise, there are some other mechanisms related to short channel effects, for example, which because of smaller oxide thickness, etc., we can have some mechanism which can lead to time dependent shifts in the devices, and they may be reversible, but temporarily they can have time dependent shifts, and which can lead to time dependent shift in the overall ADC characteristics over here. So, if you want to be accurate enough, you want to preserve the accuracy, not to miss the lower values of the signal, and have correct values coming out of the two comparators, consistent values coming out, we would like to go for cancellation of the offset. The example that we have taken, the constraints are relatively relaxed. We are assuming full swing 0 to VDD, and the delta V or the resolution in voltage domain that we are trying to see is around 15 millivolt. The offset values can be of that range, 15, 30 millivolt, you can go to that. If the precision requirements are higher, maybe 8 bit or 9 bit, there you can see that many more bits will get corrupted. So, here we have taken the resolution of 7 bit, and as a result the delta V, the analog resolution of the comparator is 15 millivolt, and the offset that you can get in 180 nanometer can be of that order, means few tens of millivolt. And in cases when we are so still here we are talking about few bits getting error or few bits having problem. But if you are having higher resolution, you can imagine, suppose you are having 10 bit resolution, and 10 bit resolution would require maybe 1 millivolt of precision, and there if you have 15 bit or 15 millivolt mismatch or 30 millivolt mismatch or 30 levels of error, that is even more drastic. Therefore, the offset cancellation will become even more crucial. So, here probably it is relatively less crucial, but still you are having 30 millivolt of mismatch, you are having 4 or 5 LSBs of error, which is not good. So, and likewise 2 comparators being used, that is also aggravating our case. So, therefore, it is important to consider this concept of offset and the techniques to cancel that offset, that is in general applied whenever we are having whenever we are targeting significant precision in our data processing. And we will along with the single ended version, we will also look into the differential version, fully differential version, and try to see how it can benefit us. That is another reason why fully differential operation is advantageous. For the comparator, we will see that if you are using fully differential version, offset cancellation can be more effective or more convenient to implement. Any question?
So, here delta weighted or V offset both are some DC values.
Yes.
So, what do you mean by the amplification of a DC value? Some gain?
DC amplification, you have DC gain, right? What do you have the amplifier characteristics, low frequency up to DC, you have some gain, right? That means if you apply a DC voltage and sweep it, or if you apply a DC voltage, of course the output voltage will change, that is DC. So, the gain of the amplifier is this, right? So, DC you have gain. If you change the DC bias input, one of them is VDD by 2, another one is VDD by 2 plus 20 millivolt, of course the output will change.
But for finding the gain, we assume that the DC point is constant. So, we take a finite GM. So, in this case the DC point is
DC bias, what you have is a small change in DC between these two, or small difference in DC can be seen as DC bias plus that delta V. That delta V is small signal. What I am saying is small signal is applicable, and we are looking at small signal gain. Small signal gain does not mean the high frequency, small signal can be DC. Any other question? So, as we have seen in the chopper, what are we trying to do? We are trying to shift the frequency toward, or the signal towards higher frequency. The 1 upon f noise is towards DC, close to DC. We do not want it to interfere with our signal. So, there also we are trying to model that noise with as a very low frequency source close to DC. Okay. So, any other questions? So, it is all these things are important to understand, and these are design issues which are very crucial. In our simulations also we will try to assess some of these and look at the associated solutions. Resume our discussion.